Hello and welcome to 11-8 from the Big Ideas book series in geometry. So we are going to do surface area and volume of spheres. All right, so the parts of a sphere. So we have the hemisphere, which is just cutting a circle in half at the great circle, meaning that the great circle would be the biggest cross-sectional area. So the center of the hemisphere, or the center of the sphere, and the center of the great circle would be the same. And the radius starts at the center of the sphere. And if you go out in every single direction from this, so if we go out in every single direction that you can go out, you can only see it on the two-dimensional thing right here, and that's what creates a circle. But if we do it from a point from your hand and go up, down, right, left, and at all the different angles, that's what creates a sphere. So it's all the points equidistant from a point in all directions, up, down, left, right, three-dimensionally, and that's what creates a sphere. If we're only in a plane, a flat surface that's two dimensions, that's when we create a circle. So it would be all the points equidistant from the center. All right, so where does the volume formula come from? And this is a big, Mr. Cavalieri here studied this, and what he studied was hemispheres having the same cross-sectional area as a cylinder with a cone missing. All right, so he compared every single hemisphere's cross-sectional area, is what he's thinking, with a cylinder with the cones missing cross-sectional area. So we're going to talk through this. It's going to be a bit confusing. So we can see the cross-section of this sphere here, of this hemisphere on the left. So if we can find the area of that one cross section, then we're going to compare it to the cross section of a cylinder with the cone taken out. So we're going to compare these two cross sections. And what Cavalieri said is if you did that at every different rate, they're all going to be the same. So let's see what happens here. So in order to find this, we need to find the length of that piece right here, because we need to take pi r squared in order to get what that area is, because we're going to compare every area here. So we need the length of this piece right here. Well, using the Pythagorean theorem, we're going to take the hypotenuse squared minus a leg squared gives you the other leg squared. But if I don't want the leg squared, I just want the leg, I'm going to square root each side. So this purple piece right here is going to be the square root of r squared minus x squared, and then we have to square that. So now what's going to happen is this square and that square root are going to cancel. So you're left with pi times r squared minus x squared. So now we're just going to distribute, and we have pi r squared minus pi x squared. So that's the area of this circle here. Okay, now we're going to go over to the cylinder, and we're saying that these heights of this hemisphere and that cylinder are the same. And also what's happening here is the height of this and the radius of this are both the same length. So what we're going to have to do now is we're going to find this whole cross-sectional, I'm going to take the whole green, okay, pretend the circle's not, and I'm going to subtract the white circle from that. And then that's going to give me the cross section of the cylinder minus the cone, or less the cone. That's why we are subtracting this here. So this is supposed to be, okay, so this is the whole green. All right, so the whole green, it looks like that is going to be pi r squared, because we know that radius is r squared. And then we don't know what that one is in the white, so we're just going to have to call it a different value. So we're going to call it pi x squared. Now, if you look, those two cross sections taken at the same place, this cross section, those two are equal. So if we did that at every place, so if we did it, here and we did it here, those would also come up to be the same. So if we did it in every single place along the way, as we get smaller up here and up, well, we'd go in the opposite. Oh, I have to go here, sorry. Here and this smaller and then bigger and then all along the way. Every way every single cross section inverted is the same. So if every cross section is the same, that means their two volumes have to be the same. So here they're going through and showing you the two cross sections, which is what I just did. So if we move this piece right here, which I can't seem to move, those two cross sections are exactly the same. So then what does that mean? That means that their volumes have to be the same. So if their cross sections are the same at every height, then their volumes will have to be the same. So what did we do? If we take the volume of the cylinder minus the cone, that has to equal what the whole sphere is. So we know how to take the volume of a cone, of a cylinder. It's the area of the base, pi r squared times height, and a cone is 1/3 pi r squared times height. Well, if you look, both of these have pi r squared height, pi r squared height. So we have 1 here and 1/3 there. So if we take 1 minus 1/3, we are at 2/3 pi r squared height. And now if you remember, I showed you that the height and the radius of that cylinder were both the same. So I can substitute in place of that height, I can plug in the r. So now we have r squared times r, which is going to give us r cubed. So this is for a hemisphere, remember we were talking about. So now if we're going to find the volume of a whole sphere, we have to double that. So 2/3 times 2 gives you 4/3. And that's how they arrive at this formula for the volume of a sphere is 4/3 pi r cubed. All right, so now let's just put this formula to use. So in here, we've got volume of a sphere is equal to 4/3 pi r cubed. So they tell us the radius here is 9, so 9 cubed, and they want us to leave it in terms of pi. So 9 cubed, and then multiply by 4 and divide by 3, and we should get 972 pi, and this is volume, so it's going to be centimeters cubed. All right, so now we're going to be introducing the formula for the surface area. Whew, a whole bunch of sides got mixed up or aren't here. What happened to the rest of these? Some slides disappeared on me. All right, so the surface area. To find this surface area, it is way more confusing, and I had a calculus screen up here to show you guys what it came from or where it comes from, but I don't seem to see it here. So with this surface area, all right, continuing on here, here's the volume. I knew I had another sample problem, and here it is. So here is a hemisphere, and they're asking us to round to the nearest tenth. So you can either use the whole formula, which is volume equals 4/3 pi r cubed, and then at the very end divide by 2 because we're only going to have a hemisphere. Or if you can recall from that formula, if you take 4/3 and divide by 2, you get 2/3 pi r cubed. So it doesn't matter which way you do it. So 2/3 pi 4 to the third power. And they do want us to round this one to the nearest tenth. So this answer comes out to be 134.0, and our label here is going to be meters cubed. All right, so the next thing here is what about the area of a sphere, the surface area here? So when we have the surface area of a sphere, there is a lot of calculus. And when you guys look in here, maybe when you guys get to the calculus class, they'll go through this with you. But I have found this is way more confusing than helpful. So I'm just going to go on and give you this formula. So the surface area formula for any sphere is 4 times pi times radius squared. So 4 times pi times radius squared. All right, so here's some problems involving surface area. And in our surface area, the first problem, find the surface area of a sphere with the diameter of 10. Well, that formula that we need is 4 pi r squared. So we need the radius. So the radius is 5 if your diameter is 10. So it's going to be 4 pi 5 squared, and they say leave your answer in terms of pi. So 5 squared is 25, 25 times 4. So our answer here is going to be 100 pi, and our label looks like it is feet. What are we doing? Surface area. So we need squared. All right, find the volume of a sphere when the surface area is 144. So if the surface area formula, is 4 pi r squared, and they're telling you that surface area is 144 pi, is 4 pi r squared. So this pi cancels with that pi, and we take 144 and divide by 4, we get 36 equals r squared. Now if we square root both sides, we get this radius to be 6. So now we want to go in and find that volume. So the volume formula is 4/3 pi r cubed. So we can fill in 4/3 pi, and our radius we just found out is 6. So 4/3 pi, 4/3 pi 6 cubed. All right, and again, we're going to leave that in terms of pi. So we're going to have 288 pi, and we're finding volume. So it's going to be meters cubed. All right, on to our last problem of the day. So the surface area, find the surface area of a sphere with a great circle. So the area of a circle, remember, is pi r squared. So this pi r squared equals your 4 pi of the great circle. So when we cross these off, we know that radius squared is 4, which makes your radius 2. So now when we're going to find our surface area, we're going to go use that formula that is 4 pi r squared. So we just found our radius to be 2. So 2 squared is 4. 4 times 4 is 16. So it looks like we're going to have 16 pi, and we're finding surface area. So it's going to be 16 pi inches squared. All right, so the first thing we went through is where the volume formula came from, but it basically boils down to you're going to use the volume formula is 4/3 pi r cubed, and the surface area formula for spheres is going to be 4 pi r squared. And remember, you can have a cheat sheet whether you're working on a quiz or a test or anything, so make sure you have everything labeled, that these are the formulas for your sphere. All right, good luck on your homework.